today we going to talk on algebraic structure, field, vector space, structure preserving map. So, what is algebraic structure? So, to understand algebraic structure, we have to first understand what is set, what is binary relation, and then algebraic structure. All of you know what is set. So, set is undefined basically, but still we know what is set. There is some axiomatic definition on set. There are 11 axioms. Sometimes we call set is a well-defined collections of well-defined objects. That is not actually true. This is not a definition. What is binary relation? So set is actually undefined concept with some axioms, satisfy some 11 axioms. What is a binary relation? We know the binary relation is like a function. It's like a function, say rho from if S is a set, say non-empty set, S cross S to S. So if take two input from S, say X and Y from S, both are from S, and give one output in S, which is also called say X row, or say it is a other composition, star or star, X star Y. Sorry, binary relation also, binary operation. Operation. Printing mistake is the binary operation. So it's a binary operation. What is binary operation? There are two elements X and Y, and we have output X compose Y. Is maybe addition or maybe subtraction, multiplication. There are several operations. So is any function from S cross S to S is a operation, binary operation. There are two elements. Now, the list structure is you can start with the S is a non-empty set, and we have as a binary operation. Just set and binary operation, but that binary operation must satisfy some equation or some relation. Satisfy some relation, and the first relation is obviously some books write is closure, but closure is not actually is not is already in the definition, because closure means this: X belongs to S, Y belongs to S, implies X star Y belongs to S. That is a closure property. Some author says, but actually closure property is just a definition. So once I say it is a binary operation, that means it is automatically closure. So the first thing we have to define the associativity. So what is associativity? All of you know that associativity is this. With all ABC actually. Yes. Now this is called something semi-group. Once there is a non-empty set with a binary operation with just associativity property is called semi-group. And then this after that we have some another property. It's called existence of identity. This identity may or may not exist. Say E is an element such that E star A is equal to A star E for all A is equal to A for all A. Then E is called identity element. Sometimes E star A equal to A, maybe A star E may not be A. In that case, we say A is the left identity. If later case, it is called right identity. Whatever we took both of them, so we call this identity element. If such an element exists, then we call monoid. So such a structure, just a structure is called semi-group. Then if semi-group with this is called monoid, some structure. Maybe something is semi-group but not monoid. Next, This is called in the existence of inverse. If for every element S, there exists an element, say A dash. Now, this E does not depend on A. This is E star A is A, or A star E is A for all A. So for every A there is single E, but here for every A there is A dash. For every A there is A dash, and you can prove if A is different or different A, we get different inverse. That is you can easily prove. If inverse is same, then the element also same. If element is same, obviously the inverse is same. So there is 1-to-1. May not exist. Obviously, they may not exist. Inverse may not exist. For some element, inverse exists, some may not exist. But the elements whose inverse exists, that's the inverse with that is a 1-to-1. And if A inverse exists, then A inverse of A inverse also exists, and that is A. What is this? The condition is again A star. If only this is happen, this is called right inverse, and if this is happen, it's called left inverse. If both is happen, it's called inverse. And the whole this thing is called group. If all properties, maybe some group may not be monoid, maybe monoid but not group. Something, say real number with multiplication. This is monoid but not group, because 0 has no inverse. In addition with this, if we have another properties, A star B is equal to B star A, that is called commutativity property. So these are 4 things we have to remember: associativity, identity, inverse, and commutativity. In every algebraic structure, these are the important part. These are important properties of this, or terminology of this algebraic structure with operation, binary operation. Now, what is group? I already discussed what is group. Group is a non-empty set. G is non-empty set with binary operation. Since it's binary, already this A star A in A G for all A star B in G for all A B in G, and with extra 3 property: associativity, existence of inverse, and existence of identity, then existence of inverse. Existence of identity is fast. So then, if identity is not exist, then inverse can't exist, because by definition, inverse A star A inverse is E. So E first must exist first. Now, if with addition of that, it is a group. We have another in group may not be commutative. If commutative part is there, then it is called commutative group. Commutative group. This is commutative. Also, some called Abelian group. The name of Abel, mathematician Abel. That you know, the Abel prize is the highest prize in mathematics. So it's called Abel. So with the name of Abel, it's the Abelian group. So up to this, we have some structure with a 1 binary operation. Maybe we can introduce 2 binary operations. One say addition and say multiplication. This may not be usual addition. 2 plus 3 may be 9. 0 plus 7 may be 2, or 1 plus 7 may be 7. 1 plus 8 may be 8. Maybe A star B, A plus B is A plus B. This next plus is the usual plus minus 1. And then one more addition is multiplication. You can say it's multiplication, also called it first operation and second operation. Say R. R is a non-empty set with 2 operations, such that this is a commutative group. With the first operation, this is commutative. Like say integer. With integer, the first operation is commutative. Everything associative, commutative, existence of inverse, identity is 0. So this commutative group under the first operation, also called addition operation. This may not be usual addition. And with the second operation, some properties are there. What is? It is associative. It is associative. So that means under the second operation it is semi-group. And some author take one include in the ring, but some author take also they took one is not in the ring. Some author call ring always is there is identity, and some author call okay it may not identity exist, but if I one is there, sometimes zero is stand for the first operation identity, and one stand for the second operation identity. It's also called additive inverse, multiplicative inverse. Sorry, additive identity, and one is the multiplicative identity. But remember, this zero may not be our zero. This one may not be our one. This one may be 5, our 5, or zero may be minus 3, minus 3 may be 0. This is zero, just notation 0. It's not a zero what we study in class 3 or 4, class 2. So this is 0 stand for this identity, and 1 stand for the multiplicative identity. Now some author take ring may not have identity. Once if 1 is there in the ring, this is called ring with identity, ring with 1, ring with identity, something like that. And some author assume that 1 is always there. So in once we read book, you should carefully note that this in this book whether ring means it is ring with identity or not. Now this first operation is a usual operation, second operation is operation, another operation. But what is the link between this? There must be some link. Otherwise, is first operation one operation, R plus is the one structure, R dot is another structure. But we structured R plus dot. So something using class and dot must be there, and this is that with using both of them, both of the operations is a distributive property. It's called distributive property. And sometimes we call the second operation is distributive over the first. ABC is always in R. ABC, once I write ABC or XYZ is always in that set, underline set. This is called the first operation is distributed over the second. It is not the second over the first. A dot A plus B dot C is not A plus B dot A plus C. That is not true. Maybe true. In generally, it is not true. Distribution means the distribution of the first operation, second operation over the first. So this is called distributive property. And once this have this do two binary operation with first operation commutative group and second operation, it is just associative, and this distributive property is there. Then this called one may or may not be there. In some author is called one is there. Some author called is may or may not be there. So this is called ring. Sometimes a Z, our usual Z with this. This is called a ring. This structure is called ring. Now, one thing is important. It's called cancellation law. So if A plus B is equal to A plus C, we know this is B equal to C. Why? Because we just add with minus B. Also, sometimes this minus A stand for additive inverse of A, and A to the power minus all stand for multiplicative inverse of A, if it exists. But once we deal with a single operation in group, maybe A to the power minus 1 notation is used. In that case, A to the power minus 1 means the inverse of that A. A to the power minus 1 is the inverse of with that in operation, binary operation. But once two operation is there, you should clearly distinguish between two different inverse. That's why we use two different notation. But if it is only one operation, say addition, say usual addition, then we can say A to the power minus 1. That means In usual operation, 2 to the power minus 1 is just minus 2. So if in Z is a group under addition. So if only there is only operation addition, then we can say the inverse of 2 is 2 to the minus 1. In that case, 2 to the minus 1 is not half. 2 to the minus 1 is minus 2. But if you use the symbol addition, or sometimes is called addition operation, is very close to say addition. Say a star b is say a plus b minus 1. Sometimes additive word is there. Then we don't write a to the minus 1. We write minus a. And for a multiplicative thing, we write a to the minus 1. It may be something complicated. A star b is say a into b plus a plus b. Then we use only just a to the minus 1 for inverse. If the two operation, then we first operation called minus a, second operation under second operation we will use a to the minus 1. Now this is easily we can just add with minus a with the left side. So in group may not be commutative, but in group this is cancellation law hold. So cancellation law hold if the inverse exists. If the inverse exists, we can cancel. This is called left cancellation. Similarly for right cancellation, b plus a is equal to c plus a implies b is equal to c for right cancellation. Now the interesting thing is the next structure. Now what is commutative ring? Again, commutative ring is there is a commutative property. Already there is in addition there is a commutative property first operation. So that means the commutative ring in second operation. So commutative ring, the previous all this true with this extra property is a dot b is equal to b. So commutative ring is, let's say Z is a commutative. Now can it make a group under the second operation? No, never. We can't make this as group under the second operation. Why? Because we can easily prove that 0 is the additive identity with multiplied with a, this is 0. Now if we assume that 1 not equal to 0, if 1 equal to 0, there is only one element. If 1 equal to 0, then there is only one. Yes, it is a ring. It is a very trivial ring. Only one element, which is 0, which is 1, everything is this. So 1 plus 1 is again 1 because it is 0. 0 plus 0 is 0. 0 to the power minus 1 is 0. The inverse of 0, additive inverse, multiplicative both is 0. So forget about this. So ring with at least 2 elements. That means 1 not equal to 0. Identity assume in commutative ring we assume 1 is there. Now this is always for all a. That means it can't be 0 some multiplied by something equal to 1. So it can't make a group under dot under the second operation. But if you just leave 0, so you can say okay, this is there exists for all a other than 0, there exists an such that a to the power minus 1 dot a equal to 1 is already commutativity is there. Or if maybe commutativity is not there, then also we can talking about the both property, and we can say okay, this is very close to group. If it is commutative group, is commutative body is there, very close to commutative group. Just a single exception, 0 has no inverse. 0 has no multiplicative inverse. So in that case, we call it as field. We call it as field. So field means this is R plus is a commutative group. R dot is very close to commutative group, just one exception. And there is a distributive property, obviously. Now, if it is field, then you can have the cancellation law. A not equal to 0. Cancellation law is there. You can cancel this again by multiplied by A inverse. Right, left, right, both. But sometimes there is some structure which is not a field, inverse does not exist, still we can cancel. That is the important part, because the inverse existence of inverse actually for the cancellation law. But if I have a cancellation law, but still this inverse does not exist, we have some structure, it's a good structure. Like Z has no additive inverse other than 1 and minus 1, multiplicative inverse. But still, cancellation law, everything is hold for Z. But what is the inherent thing that cancellation law hold? That means the existence of inverse and cancellation law is not actually equivalent. Cancellation law is slightly weaker. Existence of inverse implies cancellation law, but cancellation law does not imply existence of inverse. So actually, what implies cancellation law is this. It's called divisor of 0. If there are two elements A dot B 0, either A0 or B0, and that makes the cancellation law. If this property true, then we can say this cancellation law holds. You just take one side, take the distributive property, take A common, A dot B plus B minus C, and then if A not equal to C, B minus C is 0, so B equal to C. B minus C means B plus minus C. So if this property hold, may not be inverse edge. Just in Z it is true, then it is called integral domain. So integral domain is it is a group under addition, a commutative group, then LCD body for multiplication, identity exists, one exists, commutativity is there, distributive body is there, inverse may or may not exist, but this has no zero divisor, no non-zero zero divisor. Zero has only one divisor, which is 0. Two non-zero element cannot be multiplied and make it 0. It's called integral domain. It's a very important thing, because many structure which is not filled, many important and interesting structure, but is integral domain like Z. And next thing is vector space. Vector space is, there's one more set now. There's a S and there's one more set. It's also non-empty, such that this V and another operation is addition is there. So this is group under commutative group under this operation. And there's a one more. We need that something is interrelated with this S and V. Just S is a structure, V is another structure, but we need something is interaction with S and V both. That is called external multiplication or scalar multiplication. Like element of V is called vector, element of S, the field is called field F is called scalar, and there is a scalar multiplication, something like that. So if A is a scalar in field and alpha is the element in V, this is in V with some property, with something like this property, and this associativity is there, some associativity property, sort of associativity. Just note these operations, and also some distributive property is there, distributive through this and distributive through that with the vector. Then it is called vector space. But sometimes we want to make a vector space over some ring, but vector space is always over the field. It can't make on ring. So in that case, all this property of the vector space is true, but the underlying field is not a field. Remember this, for the definition in the vector space definition, the field property is not used here. On any property of any relation on V, the inverse of the scalar element, multiplication inverse, not used here. That means we can take just as a ring also. In that case, we call not call vector space. If R is a ring and over this there is a set which has all this property of the vector space is there, but since the underlying thing is not filled, we call it as module. And if we introduce one more operation on module, again like a multiplication. So now there are 5 operations. Something we say, how do you write? Okay, double. And there is a scalar multiplication, and there are two in scalar. Scalar product. This dot in the scalar, this dot in the plus in the scalar. This dot is in vector, scalar with vector. This is vector plus vector. This is a dot something, and this dot is not like a cross product, not a dot product. It makes 2 vector to a single vector, binary operation on a vector. In that case, called algebra. The highest structure we in mathematics is defined. 5 operations included. and with some extra property, we just avoid this thing. What are the properties of this? Something like ring property. This ring, this ring is this is again ring. The V is ring under this plus and this multiplication. The important part is this structure preserving map. Say there is a group from one group to another group. The structure preserving map means some S star B star is in G1, that must be, say, if this is a some compose, this was structure preserving map. So in ring, what will be the structure preserving? Not only plus, in ring that should be plus as well as this. And one more thing is important. In ring, we have to also define f of 1 as a 1. In field f of 1 is automatically this star, this multiplication is not the same. This plus and this plus is different because in the two different ring. It is from one ring to another ring. Remember that f of 1 is 1. And you can ask that the inverse also is a preserved, but you can easily prove that the inverse preserved. So similarly, for the vector space, we need group from is now the vector space to vector space under the same field. If the same field is there, so there is no mapping on the field to field. My field is single, one field. In module also same thing. Now is a vector space to vector space. So that means from vectors another vector space to one vector to another vector space. So any map phi, then same thing is v plus v1 plus v2 small v1 is just I use p plus for both the vector space, and obviously the scalar multiplication. I don't use anything. Anything means it is a multiplication, and this is called linear map. Actually, structure preserving map, and sometimes it's called homomorphism. Homomorphism means any structure preserving map under is a group or field or vector space called homomorphism. It's a linear map for vector space, and isomorphism, it is a bijective. It is a bijective homomorphism is called isomorphism. That means the two structures are equivalent basically. Everything is just a name is different, but the other thing is everything is same. So stop here now.